Good afternoon, viewers. I am Arvinderjit Mahmi, lecturer in Production and Industrial Engineering Department from Government Polytechnic College, Amritsar, and my subject is tool engineering. The topic today we are going to discuss is cutting forces. Mean how much cutting force is required to cut a material with the help of a press. So, in cutting operation, when we use press, as the punch in its downward movement enters the material, it need not penetrate the thickness of the stock in order to affect the complete rupture of the part. The distance which the punch enters into the work material to cause rupture to take place is called penetration and usually given as the percentage of stock thickness. So, it is always not necessary that punch should move all through the work material. What the distance it enters into the work material to affect a complete rupture is called penetration, and it is generally given as percentage of the stock thickness. So, the percentage penetration depends on the material being cut and also on the stock thickness. When a hard and stock material is being cut, a very little penetration of the punch is necessary to cause fracture. For soft material, the penetration will be greater. As you can see on the monitor, for soft aluminum, the percentage penetration for soft aluminum is 60% of T. T is the stock thickness and for 0.15% carbon steel, the percentage penetration is 38% of stock thickness, and for 0.5% carbon steel, the percentage penetration is 24% of stock thickness. The percentage penetration also depends upon the stock thickness, being smaller for thicker sheets and greater for thinner sheets. As you can see on the monitor, this is the stock thickness and this is the percentage penetration of stock thickness. Now, if the stock thickness is 25 mm, then percentage penetration is 25% of T. T is the stock thickness, and if the stock thickness is 20 mm, then penetration is 31% of T. If stock thickness is 15 mm, then percentage penetration is 34%. So, you can see with the decrease in stock thickness, the percentage penetration increases. So, for thinner sheets, the percentage penetration is more, and for thicker sheets, the percentage penetration is less. Then comes the maximum force, written as F max in kgs kilograms, needed to cut a material is equal to the area to be sheared times the shearing strength tau s in kilogram per centimeter square for the material. For a circular blank of diameter d and of thickness T, the cutting force will be cutting force will be pi d t into tau s, where F max is the maximum cutting force required to cut a material, and d is the diameter of the circular section, and t is the thickness of the sheet, and tau s is the shear strength of the material. Now, this pi d is replaced by a letter P. P stands for perimeter. As pi d represents the perimeter, so it has been replaced by P. So, P is the perimeter of the section to be blanked. If this section of the blank is rectangular with length L and width B, then its perimeter is twice of length plus width. So, maximum force required to cut a material for such a rectangular section is equal to 2 multiplied by length plus width multiplied by stock thickness and multiplied by shear strength of the material. Now, we are talking about the maximum force, but this maximum force is not desirable in the cutting operations. We are to reduce this maximum force to a minimum level. Now, the methods of reducing cutting forces. For calculating the cutting force in the last article, it has been assumed that the bottom of the punch and the top of the die block are parallel, these lie in parallel plane, and that the blank is sheared from the sheet metal by shearing it simultaneously along the whole perimeter. So, cutting is performed simultaneously along the whole perimeter. This process is characterized by very high punch forces exerted over a very short period, resulting in a shock or impulse conditions. It is usual, however, to reduce the cutting forces and to smooth out the shock impact of heavy loads. This is achieved by arranging for a gradual cut instead of sudden cut of the stock. So, for this we have two methods which are generally used. First is by shear and second is by staggering of the punches. Now, we will discuss one by one. First of all, with the help of applying shear. As we all know, the face of the punch, the bottom of the punch and top of the die, they are parallel to the horizontal plane. But when the faces of the punch or die are grounded off, so that these do not remain parallel to the horizontal plane, what are inclined to it. This angle of inclination is called shear. This has the effect of reducing the area in shear at any one time, and the maximum force is much less. It may be reduced by as much as 50%. So, what we do in case of shear, we grind the bottom of the punch or top of the die, so that these do not remain parallel to the horizontal plane, but they are at some particular angle. So, depending upon this particular angle, the maximum cutting force can be reduced to a minimum, or you can say the maximum force can be reduced to 50% when when there is no shear is on the punch or on the die. This is made clear in figure which shows the relation of cutting forces to amount of shear. Now, you can see on the monitor the first case, this is the first case and this is the second case. In this first case, this is the bottom of the die and this is the top of, this is the bottom of the punch and this is the top of the die. These are not grounded off, these are parallel to the horizontal plane. Here the shear is 0 because there is no inclination of the bottom of the punch or the top of the die. The cutting edges are parallel and in fact they are parallel to the horizontal plane. The material is cut at once on the entire perimeter, resulting in maximum load. The force diagram shows a steep rise at maximum load and then sudden load release, sometimes shear on the both press and dies as the cut is completed. In this case, the cutting action is explained with the help of a force diagram. The vertical axis shows the load and this movement of the punch. As the punch moves toward the moves into the die stock, load increases, and at this point, as this punch enters the entire perimeter of the blank to be cut, then load increases to the maximum level, and when the cut is complete, it suddenly drops. So, this is the cutting action with shock impulse. Now, this can be reduced with the help of applying some shear on the bottom of the punch. First is the case when shear is equal to T by 3, 1/3 of the stock thickness, when shear is applied equal to 1/3 of the stock thickness. Now, here you can see, first of all, this trailing edge will make contact with the strip, and when this leading edge enters into the material through 1/3 of its width, at that moment the trailing edge is going to contact the strip. So, at this moment the cutting load will be maximum. The faces of the punch is ground off so that shear is T by 3. The cutting action will start at the leading edge of the punch and then it will gradually spread to the rest of the punch. With this, only a part of the punch would be cutting at any one instant. While the maximum force will decrease, the energy needed to complete the cut is unchanged. So, the punch travel in this case will be more than in the case of A. And third case, when angle of shear is equal to the stock thickness, that is shear is equal to T. Here you can see, first of all, the leading edge will make contact with the strip. This edge enters into the entire thickness of the strip and the trailing edge at this moment is going to touch the strip when this portion has already been cut and this portion is going to be cut. At this moment the cutting force will be maximum, but as you know, you can see on the monitor that at this moment the cutting force will be maximum, but you can see the half of the blank has been cut. So, the cutting force will reduce to 50% of the maximum force. So, the force diagram will be like this, as smooth rise, and then when the cut is complete it will move like this. When the leading edge has travelled through the stock a distance t, the trailing edge will start making contact with the material. The maximum force would be at this position of the punch, and since the cut is complete, the maximum load would be about half of that when the shear is 0. The punch travel will be still greater. The provision of shear distorts the material being cut. When the shear is on the face of the punch, the blank cannot be flat, and when the shear is on the die, the piercing cannot be flat. Now, as I have told you that shear can be applied on the punch, and this shear can also be applied on the top of the die, but when shear is applied on the bottom of the punch, then the blank cannot be cut flat, and when the shear is applied on the top of the die, then piercing or hole cannot be a straight hole. So, now we are to decide which part should be given angle of shear. So, it is very clear when we are performing a blanking operation, then shear is applied on the die, top of the die, and when we are performing piercing operation or punching operation, then shear is applied on the bottom of the punch. So, for blanking operation, shear is provided on the die face, and for punching or piercing operation, shear is provided on the punch face. Figure shows the various methods of applying shear on the punch and the die. Whenever possible, double shear should be used so that two shear faces neutralize the side thrust which each sets up. It is clear from the above analysis that it is advisable to provide shear on the punches and the dies. Now, the amount of shear to be applied is a matter of compromise. Now, we started with 0 shear, then we applied a shear equal to 1/3 of the stock thickness, then we applied shear equal to the stock thickness. Now, how much shear should be applied so that a smooth operation with minimum cutting force can be obtained? It can be twice of thickness, it can be thrice of thickness. Now, how much thickness should be there? How much angle of shear should be there? Now, if shear is twice of T or thrice of T, then cutting edges of the tools will become too thin or too acute and are liable to break away easily. However, the shear must be at least equal to the percentage penetration of the material. So, in case of or you can say for getting minimum force with smooth operation, then angle of shear should be equal to the percentage penetration of the material. And the second case for reducing the cutting forces is by staggering of the punches. An effect similar to shear can be obtained by staggering two or more punches that all operate in one stroke of the press. For staggering, the punches are arranged so that one does not enter the material until the one before it has penetrated through it. In this manner, the cutting load may be reduced approximately 50%. Now, you can see on the monitor we have arranged two punches. Now, this punch enters the material only when the punch ahead of it has gone through the material during single stroke of the ram. So, from this it is very clear cutting force can be reduced 50% of the maximum cutting force. Now, minimum diameter of piercing, what does it mean? It means to what extent or to what minimum diameter a hole can be pierced without the failure of the punch. To punch a hole without the failure of the punch, the compressive strength of the punch should be at least equal to the force necessary to fracture the material. The hole which will be punched under this condition will be smallest hole. If tau s is the shear strength of the work material, sigma c the compressive strength of the punch material, d is the smallest hole diameter to be pierced, and T is the stock thickness, then piercing pressure is equal to strength of the material multiplied by perimeter pi d multiplied by stock thickness, and strength of the punch is equal to compressive strength of the material multiplied by the cross sectional area of the piercing, that is pi by 4 d square. So, when these two piercing pressure and strength of the punch are equal, then in this particular case only a minimum hole can be pierced. So, we are equating these two values. So, tau s pi dt is equal to sigma c pi by 4 d square. So, cancelling out the same quantities on both the sides, d comes equal to 4 tau s upon sigma c multiplied by T, and it is assumed that compressive strength of the punch is twice the shear strength of the material. Then putting the value of sigma c is equal to twice of tau s, we get d is equal to 2T, mean the minimum hole that can be pierced is equal to twice the stock thickness. In actual practice, smaller holes than this are pierced successfully, showing to what extent the punch may be loaded without failure. Then comes drawing pressure for drawing dies. Drawing operation is the process of forming a flat piece of material blank into a hollow shape by means of a punch which causes the blank to flow into the die cavity. Now, the depth of draw may be shallow, moderate or deep. If the depth of the formed cup is up to half of its diameter, the process is called shallow drawing. If the depth of the formed cup exceeds the diameter of the formed cup, then it is termed as deep drawing. And then what is moderate drawing? When the depth of cup is in between half of the diameter of the formed cup and to the full diameter of the formed cup, then this type of drawing is called moderate drawing. Now, you can see on the monitor a drawing operation in which a flat sheet is being converted into a cup shape. Here you can see this is the punch and this is the die. These are the these cutting edges of the punch are rounded off, and similarly these cutting edges of the die are again rounded off. These are rounded off at radius RD, mean edge radius of the drawing die, similarly RP, edge radius of the drawing punch. Before the operation the sheet is flat, and after the operation the sheet has been converted into a cup shape or a glass shape. Here RD is the edge radius of the draw die over which the blank is drawn. If this radius is too small, the resistance to flow of the metal increases, resulting in cutting or tearing of the metal. On the other hand, too large a die radius may induce the formation of wrinkles in the metal as it is drawn into the die cavity from beneath the blank holder. This radius RD usually ranges from 4 to 10 times of the blank thickness. So, edge radius of the die is in between 4T to 10T. Similarly, RP mean punch radius, edge radius of the punch is also very critical. The edges of the punch must be rounded off to avoid cutting or tearing the material. An excessive punch radius increases the tendency of the material to buckle. The punch radius should be 4 times the stock thickness. So, edge radius of the punch should be equal to 4 times the stock thickness. Then comes how much drying pressure is required to form a flat sheet into a glass or cup shaped. The force needed to draw a shell is equal to the product of the cross sectional area and the yield strength in tension of the work material. For a cylindrical shell, the drawing force can be determined by the formula F is equal to pi dt sigma ut d upon d minus c, where d is small d diameter of the cylindrical shell formed and sigma ut ultimate tensile strength of the material, and T is the thickness of the strip. The term d upon d takes into account the relation between blank and the shell diameter, and C is a constant. Its value ranges from 0.6 to 0.7, and it accounts for friction and the bending effect. Then comes the blank holding pressure.